Imagine something in space so incredibly dense that just a teaspoon of it would outweigh mountains. Picture a gravitational pull so fierce that nothing, not even light, the fastest thing we know, can escape. These aren't just nightmares from science fiction. They're black holes, and they're out there, lurking throughout the cosmos, silent and seemingly insatiable. They're often called the universe's ultimate monsters, born from the death of giant stars or from strange conditions in the early universe, and they just keep growing, patiently and relentlessly. But what if that growth never actually stops? What if their hunger truly has no limits? We spot these giants at the hearts of galaxies, some weighing billions of times more than our own sun. We've even seen them merge, becoming even more massive. They act like cosmic vacuum cleaners, but not in the way you might picture. They don't just suck things in from miles away. Instead, anything that drifts too close and crosses their point of no return, the event horizon, is gone forever. So a chilling question echoes through the vastness of space. Will these celestial behemoths, these ever-expanding maws of darkness, eventually gobble up every star, every planet, every galaxy, until nothing else is left? Could the ultimate fate of our universe be to get eaten, piece by piece, by these gravitational titans? To even start answering that, we need to get a grip on what black holes are, and how they get so enormous. A black hole is a spot in spacetime where gravity is so overwhelmingly strong that nothing, no particles, not even light, can get away. They're what's left after massive stars run out of fuel and collapse under their own immense gravity. If the star is big enough, this collapse squishes all its matter into an unbelievably tiny point called a singularity, and voila, a black hole is born. Then there are supermassive black holes, the kind found at the centers of most galaxies, including Sagittarius A in our Milky Way. These can be millions to billions of times the mass of our sun. We even got our first direct picture of one, in the galaxy M87, which was a stunning confirmation of their existence. So how do they pack on the pounds? Black holes aren't just sitting there, they're dynamic and can grow in a couple of main ways. First up is accretion. Think of a cosmic whirlpool. A black hole pulls in nearby gas, dust, and sometimes even unlucky stars that wander too close. This material forms a swirling, superheated disk around the black hole, known as an accretion disk. As this matter spirals inward, it heats up to incredible temperatures, blasting out intense radiation before it finally crosses that event horizon and adds to the black hole's mass. We've learned recently that some supermassive black holes in the early universe grew incredibly fast through intense feeding frenzies. In fact, some black holes have been caught eating material at rates that seem to break the supposed rules, like the Eddington limit. That's the theoretical speed limit for how fast a black hole can chow down before its own radiation pushes the food away. One black hole, Lid 568, which was around when the universe was just 1.5 billion years old, seems to be gulping down matter at more than 40 times this limit. The second main way they grow is by merging. Over cosmic time, galaxies often bump into each other and merge. When this happens, their central supermassive black holes can spiral towards one another, eventually combining into a single, even more colossal black hole. These mergers are universe-shaking events, sending gravitational waves rippling through space-time waves we've actually detected here on Earth. For black holes that are already over about 100 million times the sun's mass, studies suggest that mergers might actually be the main way they grow, more so than just steadily sipping on gas. So these cosmic titans are always looking to get bigger, either by munching on nearby material or by teaming up with their own kind. This constant growth is a basic part of what they are, painting a picture of them having an ever-increasing say in their cosmic neighborhoods. Astronomers have even found some new tricks up the universe's sleeve, like spiraling magnetic winds that might help supermassive black holes bulk up, kind of like how similar winds help baby stars grow, just on a mind-bogglingly larger scale. If black holes are always growing and some are growing astonishingly fast, it naturally leads to a rather unsettling thought. What's the endgame here? If they relentlessly pull in everything around them, could they, if you give them enough time, eat their entire home galaxy? And if they can polish off a galaxy, what about a whole cluster of galaxies? Could they ultimately devour all the matter in the entire universe? This is the big dramatic question that keeps scientists digging and gives the rest of us a little shiver of existential dread. Picture a supermassive black hole like Ton 618, one of the most massive we've ever spotted, clocking in at around 66 billion times the mass of our sun. It's already a giant. Now imagine its growth over not just millions but billions or even trillions of years. As it eats stars and gas, its gravitational influence, its ability to grab matter that strays too close, increases with its mass. The event horizon, that point of no return, gets bigger as the black hole's mass goes up. More mass means a bigger mouth, able to swallow larger chunks of the cosmos. Think about the timescales we're dealing with. The universe is currently about 13.8 billion years old. Stars will probably keep forming for another 100 trillion years or so. Black holes play on even longer timelines. If a typical supermassive black hole kept eating at the rates we see now, it would take way longer than the current age of the universe. Maybe more than 1 trillion years, or about 100 times the universe's current lifespan, just to consume the matter within its current potential reach, and that's not even counting other factors. But what if enough time is a massive understatement? We're talking about cosmic eras so far in the future that the current age of the universe would seem like just a blink. In these distant futures, as stars use up their fuel and die, the universe will get darker. More and more of its matter will be locked up in stellar leftovers like white dwarfs, neutron stars, and of course, black holes. In this degenerate era, black holes would pretty much be the main gravitational players in many areas. If their growth just continued, unchecked, it's easy to imagine a grim scenario of a universe slowly being eaten from the inside out, galaxy by galaxy, each galactic core a monstrous black hole expanding its dark reach, eventually leaving behind nothing but black holes. And then, maybe these black holes themselves would start to merge across what used to be empty space between galaxies. This vision of a universe slowly giving in to an all-consuming darkness is where their relentless growth seems to lead if you take it to the extreme. It's a mind-bending scenario, isn't it? Before we explore what science actually predicts and whether there's anything to stop this cosmic feast, if you're finding this journey into the heart of darkness fascinating, go ahead and hit that subscribe button and ring the notification bell. That way, you won't miss our future explorations into the deepest mysteries of the cosmos. So, are we all doomed to become black hole chow? The dramatic image of a universe being entirely consumed is certainly attention-grabbing, but thankfully the cosmos has a few key defenses up its sleeve. First, and probably the biggest game-changer, is the expansion of the universe. Not only is the universe expanding, but this expansion is actually speeding up, driven by a mysterious force we've nicknamed dark energy. This means that galaxies, and the supermassive black holes at their centers, are generally moving further and further apart from each other. So, while a black hole might be able to clear out its local cosmic cul-de-sac, those vast cosmic distances are constantly increasing. Matter beyond a certain point will be carried away by this expansion faster than any black hole's gravity could ever hope to pull it back. The universe's own growth acts as a natural speed bump, limiting how much any single black hole can ultimately eat. Secondly, there seems to be a practical upper size limit for most supermassive black holes. While some wild theories propose stupendously large black holes, or slabs, with masses over 100 billion suns, most supermassive black holes we've actually seen seem to max out at a few tens of billions of solar masses. As a black hole gets incredibly massive, the accretion disk, its dinner plate, can become unstable. The intense radiation blasting out from this disk can create an outward pressure, known as radiation pressure, which can actually push away gas and dust, effectively cutting off the fuel supply. A black hole can get so bright from its feasting that it essentially chokes itself, stopping it from just eating uncontrollably. Plus, if the accretion disk gets too big, the material in it might just decide to form stars instead of feeding the black hole. The third, and maybe the most mind-bending counter-argument, comes from the black holes themselves: Hawking radiation. Back in 1974, Stephen Hawking came up with a revolutionary idea that black holes aren't completely black. Because of quantum effects happening right near the event horizon, black holes should slowly leak particles. This radiation carries away energy, and since energy and mass are two sides of the same coin, thanks Einstein for E=mc2, the black hole slowly loses mass. It evaporates. Now for the supermassive black holes we're talking about, this evaporation is unbelievably, ridiculously slow. A black hole with the mass of our sun would take something like 10 circumflex 67 years to evaporate completely. A supermassive black hole weighing 100 billion solar masses might take around 2x10 circumflex 100 years. To put that in perspective, the current age of the universe is a tiny 1.4x10 circumflex 10 years. So, right now, and for ages and ages to come, black holes will grow way faster by eating than they'll shrink by evaporating. But, in the very, very distant future, when the universe is cold, dark, and all the stars have long since burned out, and all nearby munchies have been consumed, Hawking radiation will finally take center stage. Every single black hole, no matter how huge, is predicted to eventually radiate away all its mass and just disappear. The biggest black holes we can imagine could take up to 10 circumflex 106 or even 10 circumflex 110 years to fully evaporate. So, what does this super distant future look like? If the universe keeps on expanding and accelerating, galaxies will become isolated islands. Eventually, all stars will burn out. Black holes will have a long feast on the leftovers. But then, isolated and with nothing left to eat, they'll begin their slow, multi-eon disappearing act. The universe would become an increasingly diluted, cold, and dark place, eventually filled only with stray photons, neutrinos, and other basic particles as even the black holes fade away. There is another idea, though it's considered less likely, called the Big Crunch. If the universe's expansion were to somehow reverse, it could all collapse back in on itself. In that dramatic ending, black holes could indeed merge, maybe even forming one ginormous black hole as the universe implodes into a final singularity, perhaps even triggering a new Big Bang. But what we see now strongly points towards continued expansion, making the big freeze and the eventual vanishing of black holes the more probable long-term fate. So, while the scientific forecast suggests black holes won't eat the entire universe, plenty of questions and fascinating mysteries are still out there. We're still intensely studying exactly how some of those early quasars manage that super Eddington accretion eating way faster than they supposedly should. How did the very first seed black holes even form, the ones that grew into the supermassive giants we see so early in cosmic history? Did they come from the collapse of the first generation of massive stars, or did enormous clouds of primordial gas collapse directly into them? Some theories even float the idea that those stupendously large black holes or slabs might be ancient relics from the early universe just hanging out outside of galaxies, though we don't have any direct proof of them yet. And the nature of dark energy, the force speeding up cosmic expansion, is still one of the biggest puzzles in physics. Its future behavior is key to figuring out the universe's ultimate destiny. Some newer, more out-there theories even try to link black hole growth to cosmic expansion itself, suggesting black holes might actually contain dark energy and somehow couple to the universe's expansion. A concept that could totally reframe their role in the cosmos. And what about Hawking radiation? It's a cornerstone of theory, but it hasn't been directly seen yet, mostly because it's predicted to be incredibly faint for the black holes we can actually observe. However, some recent studies hint that tiny morsel black holes, possibly created during black hole or neutron star mergers, might emit Hawking radiation that we could actually detect. Confirming it exists would be a huge leap forward in trying to bring together general relativity, the science of gravity, and quantum mechanics, the science of the very small. So, back to our big question. Will black holes eat the entire universe? The current scientific thinking is a pretty firm no. While they are definitely cosmic monsters that relentlessly consume matter and can grow to truly astounding sizes, they're ultimately kept in check by the sheer vastness and the accelerating expansion of the universe itself. They're also limited by their own feeding mechanisms, and on timescales that are almost impossible to truly grasp. They are destined to simply fade away through Hawking radiation. Instead of being the devourers of everything, black holes are essential players in the grand cosmic story. They shape galaxies, influence where and when stars form, and, in their final act, slowly return their borrowed mass and energy back to the universe. They represent the extremes of gravity and the very edge of our understanding, reminding us that the universe is a place of constant change and evolution, with a future far stranger and longer than we can really wrap our heads around. The darkness they represent isn't an all-consuming end, but rather a fascinating part of an immense ongoing cosmic cycle. What are your thoughts on the ultimate fate of black holes in our universe? Do you find their immense power more terrifying or fascinating? Let us know down in the comments. And if you want to keep exploring the universe's biggest questions with us, don't forget to like this video and share it with your fellow cosmic adventurers. Thanks for watching.